We know very well that in the frequency domain, current and voltage are conveniently defined using phasors as shown. In the last two videos, we've considered power in the time domain. Now it's time to consider power in the frequency domain. Since phasors are complex numbers, we anticipate that power expressed in the frequency domain will be done with complex numbers. Here is the equation which may be used to calculate the complex power associated with an element. In the equation, S phasor is the complex power associated with a given element. While the equation is essentially a voltage times a current, the typical unit used to denote the complex power is not watts. Rather, it is the volt amp. This is done to help reinforce that one is talking about complex power, which in general will have two parts, a real part and an imaginary part. In this snapshot, we seek to understand why complex power is defined by V phasor times I phasor conjugate divided by 2, and in the process see how complex power is related to the power we have considered in the time domain. We'll find it instructive to see how complex power relates to impedance. Here again is the expression for calculating complex power. Let's manipulate the equation a bit to see what we may find. V phasor is just some amplitude, Vm, and an angle, theta v. We use the conjugate of the phasor current, and so we have what? Im angle minus theta I. The minus sign associated with theta I comes by virtue of the conjugate. This is the product of two complex numbers. Their net amplitude is the product of the amplitudes, and their combined phase angle the sum of the two phase angles. Therefore, we can write S phasor equals Vm Im over 2 angle theta v minus theta I. Sometimes one will see complex power written in terms of effective or RMS value. Recall that we found for sinusoidal voltages and currents that the RMS value is simply the peak value divided by square root of 2. What is the last complex power equation in terms of RMS quantities? Well, it's simply VRMS, IRMS, angle theta v minus theta I. Again, units of volt amp. For further insight, let's convert the polar form of the complex power equation to rectangular form. The rectangular form has a cosine and j sine terms. Stare at the equation for a minute. Where have we seen the first term before? This first term is what? This was the average power from a previous video. Good. So the complex power does relate to the time domain expression. Its real part is the average power. The formula does seem reasonable. The imaginary part is typically denoted with a Q. Therefore, we write complex power is P plus JQ. As just noted, P is the average power, as we know from that previous video. It is quoted in watts. Q is the so-called reactive power. Reactive power describes the rate of energy transfer into and out of reactive elements. To distinguish Q and P, the unit of Q is the var, which denotes volts, amps, reactive. There are many definitions associated with power in the frequency domain. Let's make a few more observations regarding complex power. The average power is the real part of the complex power. Recall that average power is associated only with resistance, as due to the 90 degrees of phase difference between current and voltage for inductors and capacitors, pure energy storage elements dissipate zero average power. This does not mean that power associated with inductors and capacitors is inconsequential. Let's look at the second term from the complex power equation. This term has the sign and not the cosine of the phase difference between voltage and current. Therefore, while reactive power is 0 for pure resistors, it is not 0 for inductors and capacitors. Remember that the sign is an odd function. Therefore, while sine of theta v minus theta I equals positive 1 for a pure inductor, it's negative 1 for a capacitor. Therefore, inductors exhibit positive reactive power, theta V minus theta I equals 90 degrees, and capacitors exhibit negative reactive power. Theta V minus theta I equals negative 90 degrees. So again, the inductor is going to have the positive reactive power and the capacitor negative reactive power. Please don't get the idea that since reactive power is associated with the imaginary component that it's fictitious or unimportant. In the next video, we'll begin to see the importance of reactive power. It should be noted that complex power is conserved. Mathematically, we write the following. So we're summing the complex power over k units. So that's the sum of what? V phasor k, I phasor k conjugate over 2. Breaking this into real and imaginary parts, we find that the sum of the average power associated with all elements must be 0, and so too the sum of the reactive power. It is also helpful to relate complex power to impedance, and we attempt to do this now. Recall that impedance is simply the ratio of the phasor voltage to the phasor current for a given element. Notice how the angle of the impedance is the phase difference between voltage and current. This phase difference shows up in the complex power equations, and so relating complex power and impedance should be straightforward. To do this, let's express impedance in rectangular format. In rectangular format, we can clearly identify the real and imaginary parts. We know that average power is related to the resistive impedance and reactive power to the reactive impedance. We formalize this relationship on the next slide. Here I show the rectangular forms of the impedance and the complex power. We often speak of I squared R power when talking about resistors. Let's now think in terms of I squared Z. Thought of in this manner, we have the following. Really, all we're doing here is using Ohm's law in the frequency domain to replace Vm with Im times the real part of the impedance and then the imaginary part of the impedance. Here is just another way of identifying average power with the real part of the impedance and reactive power with the imaginary part of the impedance. We can't introduce complex power without thinking about the complex plane. We do that next. Shown here are the so-called impedance and power triangles, simply plots of the impedance and complex power on the complex plane. Visually, we see how the average power P is related to the real part of the impedance R, and how the reactive power is related to the imaginary part of the impedance. As we have noted several times now, the complex power shares the same angle as the corresponding impedance. We have one final term to introduce, the apparent power. The apparent power is simply the magnitude of the complex power. Why is it called apparent power? Notice how it is the product of the effective values of the voltage and current waveforms. If the voltage and currents in the circuit were not sinusoidal, but rather DC, Vrms times Irms would apparently be the power absorbed. This apparent power is realized when dealing with sinusoids only if the impedance in question is purely real. That is, if theta V minus theta I equals 0. A non-zero phase angle does not allow one to realize the full apparent power available. I want to close this video leaving you with a couple of questions to ponder on your own. Take a few minutes and sketch the location of a pure inductive impedance on the complex plane, and on a separate figure, sketch the associated power. This really shouldn't be too difficult. Then, imagine that the inductor is in the series RLC circuit that we considered in the phasor diagram video. What happens with complex power at resonance? Again, sketch both impedance and complex power plots.